Hello everyone. Welcome to our first 5-axis post-processing class. My name's Colin Gilchrist. I'll be your instructor. Over the course of this next month here, we're going to be going through and learning how to set up and edit the Generic Fanuc 5x mill post. We've talked a little bit before I started this recording about the direction of post development, what's going on. This post has been around for a long time. There really haven't been any significant changes to the PST portion since probably X5 or so, maybe X6, with the way that we've changed some of the parameter processing. So this post will not only work for today's current version of Mastercam, even though we would have to update it, we can still take this post and have it be compatible with X6 and up. I'm going to select the PST file and we're going to open it. Now, I've got my system set up to automatically open PST files in the Mastercam Code Expert Editor. Hold on one sec, guys. Okay. Let's see. So, Don, you've got a download link that I just sent. I should have just sent it to everybody, I believe. Should have it now. So Jeremy got it. I think everybody else should have it. And to be honest, you guys don't need to worry about downloading all the stuff right now the second. I just wanted to be sure that the link did go out so that you can download it. The basic format of this class is that I'm going to go through and lecture on how the post works and do live demonstrations and explain the functioning of the post processor. We're going to look at how the post processes NCI data and turns it into NC code. Then we're going to go through and take the generic Fanuc 5x mill post, make new copies of it, and name it for a specific machine. And then we're going to go through and configure the post to output code for that specific machine. We're going to do this with both a Gantry, which is a head style machine, and a Trunnion, or a table style machine. So you'll get to see me go through and configure it for these two different machine types. We're also going to look at how do we set up simple test files to look at the output of the post processor and determine if it's correct. And if it's not correct, how do we change it? So how do we actually make it fit the real world and the real machine? So that's going to include setting rotary limits. It will include controlling the post processor by using miscellaneous values. So miscellaneous integers and real numbers. This particular post, the generic Fanuc 5x mill post, has been around for a long time. It was basically first created right around Mastercam version 9. And the idea behind it... Hold on one sec, guys. Okay, got that taken care of. The idea behind creating this post was to put all of the 5-axis math knowledge to work behind the scenes and create a series of variable switches. And these variable switches are used to configure and change the output of the post processor by changing the value of the number. So whether the switch is 0 or 1 or 2 or 3 tells the post processor internally to make different configuration changes. This is part of the reason you'll see that with the PSB file and the PST file, the PSB is huge. It's 268 kilobytes. And this version of the post file is only 88 kilobytes. If you were to unencrypt all of the binary binned logic inside the PSB file, the post ends up being about 10,000 lines of code. It is monstrous. And if you know how the post functions and the order in which it does its calculations, it's possible to override the output, because all of the output comes from the PST file. So the PST file is generating every actual line that gets written to your NC code output. There are, however, moves that can be generated mathematically inside the PSB. So why would the post output motion that is not shown in the Mastercam file? Anybody got an idea? Nick's got one. Or Husker, I guess. Husker's got one. Safe repositioning is a function that is built into the post to allow automatic retract and movement around an imaginary box when repositioning from one tool plane to the other. Mike also brings up a good point. Some math equations have multiple correct solutions, and that is true. The other mechanism that is built into this post is a breakup routine for hitting a limit. So when we hit a rotary limit, what do? On a Trunnion style machine, the answer seems a little more simple, because on those machines, typically the tool is vertical, it's aligned to the Z-axis always, and we just retract the tool. On a Gantry style machine, however, we run into some serious problems. The post itself has a routine that's built into it to detect when we hit a rotary limit, and when we hit the limit, it will automatically retract the tool along the tool axis vector out of the cut, unwind the head, and then reapproach back, hopefully, along the same vector and continue the cut. Now that typically means you're going to get a little gouge mark on the part, but it also means that hopefully the machine will be able to continue on cutting the workpiece without simply stopping and telling you, error, we've hit the limit, and then you're stuck, because now what do you do? So this post has a lot of functionality that's already built into it, and this class really is about understanding, first and foremost, how to configure the basic switches in the post to get basic output. And then, second, to learn how to control the output of the post using the miscellaneous integers and real numbers. For class format, by the way, we start at 7:30. We're scheduled for 2 hours of lecture, and we typically take about a 15-minute break in the middle. So I typically go for an hour, we take a 15-minute break, and we come back and we go for another hour. I kind of mentioned in the email, scheduled at like 7:30 to 10 instead of 9:30. Give us that extra little bit of time, because there's also usually questions at the end of class. So my past classes, I've said, hey, it's 7:30 to 9:30, and then we end up going almost till 10 anyways. So I figured I might as well, A, be honest, and B, get you guys prepared so that, if you're planning something after class, to know that class really goes about 30 minutes longer than it says on the site. Okay, the other thing that I've put in the post-processor folder on the Dropbox is a copy. Let me make sure it's in here. The generic 5-axis generic post PDF. This PDF file, I'll go navigate to that now. So we base a lot of this class on the content that is inside this PDF file. This presentation is designed as a guide for setting up the generic 5-axis posts. And really the only thing you need to make post edits is a text editor. You can use Notepad, you can use PFE32, you can use Simco. However, I recommend you don't. I recommend that you use the Mastercam Code Expert editor. So I'm going to go to that in Mastercam 2017 to show you in general where it's located. If you go to your C drive or wherever you've installed Mastercam and go to Program Files, I'm in Windows 10, by the way, so as long as you're Windows 7 or above, it's going to be the same. If you're less than that, then I don't even think Mastercam 2017 will run. I think it requires at least Windows 7. But we go to Program Files, the install folder name. So if you're in an older version of Mastercam, MCAM X8, MCAM X9, or in this case, MCAM 2017. I'm going to double click on that. From the Mastercam 2017 folder, we're going to go into Extensions. And inside the Extensions folder is where you'll find the executable for Code Expert. And it's going to be the same if you go, X8 or X9. Like if we go back into X8, for example, and then we go to Extensions, you're also going to see Code Expert. So 2017, Extensions, Code Expert. So you can launch it directly from here. You can make a shortcut on your desktop. So if you right click and do send to, let's see, desktop, create shortcut, you can pin it to your taskbar. I do that, but the other thing that I do is I go to the post files themselves. Oh, and Mark brings up a good point. It's in your Windows Start menu too, under Mastercam. So there's a link to Code Expert right here as well. Thanks, Mark. That's a good point. The other thing we can do is go look in our shared folders. So if I go to C, Users, Public Documents, and then I'll go to Shared MCAM 2017, Mill, Posts, normally if you go and double click on a PSD file, it'll give you some error about Outlook. You have to open Outlook files from within Outlook because it thinks that this is a mailbox extension for Microsoft Outlook. If you right click, you can do Open With, And if you don't see the code expert there, you can choose another app. And this is the same process as we went through to manually get to the executable. So we go choose another app, more apps. Eventually you get to look for another app on this PC. And this is where you get to browse. So once again, C program files, MCAM 2017, or your version of Mastercam, extensions, code expert. And you can tell it with a little checkbox you want to use this program to open, files with this file extension by default. The reason I recommend you use Mastercam Code Expert is simply for the autocorrect functionality. When we look at variables that are predefined or already exist in the MP language, there has been some functionality added where we have a list of all these predefined variables that are held in the background by Mastercam Code Expert. So if we look at this variable here, we know it's a variable because it starts in the first column and because there's a colon sign to initialize the value. What we don't see is a dollar sign. So the dollar sign is only present or only used on predefined variables. And if we happen to misspell that predefined variable, you'll notice that the auto highlighting, or the blue color, which is the default for all of the predefined variables, no longer shows up because I've misspelled it. If I were to run the post right now, I would get an error at line 228 because this post has a variable that's been incorrectly spelled. If I go to start typing the name of a new variable, whatever letter I start with acts as a filter. So by starting with the letter T, you'll notice I get all of the predefined values that start with T. And I say values because down in this list down at the bottom, we actually have filters. We have filters for post blocks, strings, variables, or numeric variables, operators, and functions. So those are the 5 different types. In the case of the T variable, you can see that all of these are numeric variables. T underscore origin underscore X, T underscore origin underscore Y, T underscore origin underscore Z, T underscore WCS underscore M1 dollar sign. So each of these variables is predefined. So it already exists in the MP language. This list is not editable, and it's not editable because these variables are all defined inside MPDLL. MPDLL is the post engine. It is the set of libraries and functions that runs to open up your NCI file, open up your post file, build an instruction and variable list, and process and output the data. So all of these things are predefined. You'll notice turn and TList are operators. So if I turn off variables here, the only other things in the list is tan. And you'll notice when I select that variable, function, post block, whatever, that item in the list, I get this little help bubble that pops up. So this tells me for tan, tangent, return tan A, returns the tangent of angle A. So this is a function that I can use to return the tangent of a number. That number happens to be represented by a variable here in this description. And it is going to take that tangent value and it is going to load it into whatever my return variable is. So I've got a variable on the left that receives the result of running this trig function. If I select turn, you'll notice it says operators intersection. Cycle stack records. Moves last record to the top and shifts all other records down. Return equals turn, open parenthesis, n comma, mode, close parenthesis, where n is the number of the stack and mode is the function mode. See documentation. Returns 1 if successful, 0 if failure. So the turn function is used when we're creating a stack, which is a data structure. T-list, get tool list info. Return equals T-list n comma x comma y. Returns tool list information. The value of n determines the function state. X and y depend on the selected function state. So whenever we see instructions like this, this is just a quick help tip. It's very useful because it gives us a description of what the variable, the operator, the function, the post block does. But generally, we're going to need to go and look in the documentation and dig deeper when we see something like this. The point I wanted to make, however, is that the Mastercam Code Expert Editor has all this stuff built in specifically for editing post processors. So my recommendation to you, if you want to edit posts, is to use Code Expert. There are plenty of people who, mess around with Simco, or they mess around with Notepad++ or some other text editor to try and duplicate this functionality. Personally, I think that's a waste of time. Honestly, there's so much stuff that's built into Code Expert for editing the MP post language. Just stick with it. Okay. If I start with A, now we get a list of all the stuff that's, starts with A. And in fact, this is just all the math operators because I've got variables turned off. And there are no post blocks that start with A and no strings that start with A because all post blocks start with P, L, or M, and all strings start with S. If I turn the variables back on and I turn operators off, these are all the predefined variables that start with A. Almost all of the predefined variables either get their value directly from the NCI or they are calculated by MP from values that come from the NCI file. The exception to that rule when it comes to variables is command variables. And a command variable is actually shown to us right here. Debugging and factory set program switches. Bug $4. This variable is for debugging information, and it controls whether the values are rounded or not. So normally when you have bug 4 set to 1 and you put a tilde operator in front of a variable, you get the rounded output. If it's set to 0, you're going to get the value of the variable with format statement number 1 applied to it. So format statement number 1 is the default format statement. Okay, default format statement for English and metric, which means if your variables are not formatted for output, this is the format that they are going to hold internally while the post is processing. So it's 8 decimal places for inch values, 7 decimal places for metric. if I go back up to bug 4 here, so 0 will apply format statement 1. A value of -1 for bug 4 will output the debugging value as the raw value. So with no rounding applied whatsoever, whatever the default input was, it will output it as that. This is an example of a command variable, because what we're doing is we're setting a state here, and this affects how MP is going to process data. And the same is true for most of these guys as we move down the list. MP executable process controls. So this tells you right away these variables control how MP processes data. Tool table, it's a very important one. Pre-read, call the PWRTT post block. With these older style posts, and I don't want to say older style posts because it's still current, but with this Mastercam X series that used the generic Fanuc 5x mil post, we were kind of limited in the way that we processed NCI data. By default, we only get one processing loop. So we open the NCI file, we read 2 lines at a time, and based on the data that's in the NCI file, we output NC code. Well, then people wanted to add tool tables up at the top of their post. They wanted a list of all the tools that are going to be used in the program. So they modified MP, and they added this tool table variable, which will allow us to do a pre-read loop. And the pre-read loop essentially scans through the whole NCI file, and it gathers data at the tool changes. In general, it skips motion. So it's not looking at your GO, G1, G2, G3, or G11 moves. It's skipping past that, and it's looking at the tool changes. And for every tool change it comes across, it calls PWRTT. Now, PWRTT is a post block that is predefined, so it actually has a $sign at the end of it. And we come across this little bit of logic here. This is an if statement, and there are 3 conditions. So if the result of all 3 of these is true, and it has to be all 3 because it's tied together with the AND Boolean operator, we end up calling P tool table. And if we look at P tool table, this is the code that outputs each line to our tool table output. So as we're scanning through the NCI file, at every tool change, we look to see, is this a new tool, or has this tool been used before? And if it's a new tool, we call P tool table. If the tool has been used more than one time, we skip the call to P tool table. And how do we do that? We do that with a little bit of trickery inside MP. So what happens is MP DLL scans your NCI file, and the first time it finds a tool in the pre-read loop, it will sign the tool number positive. So if I'm using tool 5, the value of T $sign will be 5.0000000, whatever, however many decimal places. It's 5 point and then a bunch of zeros. The next time we come across the tool number in the NCI data, MP automatically signs the tool number negative. That's why we have this clause, this little statement that says, and tool $ greater than 0. So if the tool number is positive, we end up calling P tool table. This little bit of logic right here prevents the call to P tool table at every null tool change and every time a tool is used later in the program. So what this allows MP to do is to filter through all of the tool changes and only put in a single line in the tool table for each first occurrence of any given tool number. So something to be aware of as we process tool table data from the NCI with PWRTT. Okay. So in general, we're going to be following this 5-axis PDF file, going through the information that's presented here to understand how the generic Fanuc 5x mil post works. There's no real table of contents, so we're just going to scan through it real quick to touch on what are some important things to know about that are in this guide. And the reason I do that is so that if you want to, you can kind of look ahead and read through this when we're not in class. You know, sometimes I get guys in here and they're like, okay, great, I'm in the 5-axis post class. I need to write a post for this incredibly complicated machine tomorrow. I'm just like, okay, well, you know, we'll go through and talk about how all this stuff in the post works, and try to give you as much knowledge as possible. It's gonna be a bumpy road if, you know, you've got to do a 5-axis post for an incredibly complex machine, you know, and they need it tomorrow. So just a heads up on that. You know, this class is designed to give you as much stuff as you can absorb, but there's a lot to go through. Okay, so just be aware of that. So in the beginning, we talk about what types of machines does this post support. And there are actually 6 different types. There are the 3 standards: table, tilt head table. This is where one of your rotaries is on the spindle, one's on the table, and head. It also supports those same configurations in a nutator configuration. What is a nutating machine? A nutator is where one of the rotaries is not perpendicular to the center line of the other rotary. Typically, they are aligned at 45 degrees to each other. So this generic post has all of the logic to not only configure for this machine type, but support the rotary axis limits and all of the breakup of motion routines and all the other stuff for all of these different machine types. It's a pretty cool feat of engineering, the amount of stuff that they were able to cram into this post. The trick is, how does it all work? Right? I mean, that's the whole point of this class, is to kind of take you through all of the functionality that already exists, that's already available to you, and know how to set it up, know how to configure it, know how to control it. And that's the goal of this class. So in this beginning section, I'll take you through that pretty quick here. We talk about configuration. We look about how we think about how are we going to set up our part, how does the rotary axis motion on the machine occur. And we'll go through this kind of in detail. And we end up setting some variables that dictate the kinematic structure of the machine. So we set the post type variable. We define the rotary axis with rot axis and rot-dir 1 and 2. Again, I'm just skipping through this to kind of give you an idea of what's included in this guide, and then we'll go back and kind of take it slow. How to correct rotary axis direction, valid plane selections, rotary axis output options, rotary addresses, and then we get into rotary limits. So what type of motion is the machine capable of, and where do we need to stop, and what are the triggers for that internally. Then we talk, after rotary limits, we talk about axis offsets. And this occurs when we have, on this rotary table, two rotary axes that aren't necessarily perfectly on centerline. This is kind of an exaggerated schematic, but this is true of most trunnions. Okay, there's typically some kind of offset between the face of the rotary platter and the A or B axis, and there's typically some kind of shift in either X or Y from the center of the rotary platter to the center line of that secondary axis as well. So the post has some variables to account for that. This talks about the rotary axis offsets. Feed options. So we'll talk about program feed rate, inverse time on 5-axis continuous, and inverse time on only motion with rotary. So what are the different options there for feed? We'll get in a little bit near the end of class. We'll get into top map, and top map is used for outputting tilted work plane. So Fanuc, that would be G68.2, or in some cases just G68 if you're only doing a single axis rotation, but normally for 5-axis you're doing G68.2. Cycle 800 on a Siemens. And I used to know what the Heidenhain one was too, but it's been a while. So, but this functionality of top map allows us to map and output the codes for tilted workplane. For head table and head machines, the post supports tool length calculations. Many machines these days automatically compensate for tools with different lengths in a 5-axis cut. Prior to tool center point control being an option, we didn't have that luxury. And what that meant is that for an older setup or a control that doesn't have these newer options, you have to precisely know the pivot distance from the pivot point to the tip of your tool. And you have to be able to plug that into the post, and the post uses that to calculate and track the position of the tool tip with the correct rotary angle output. And when you end up changing tools, you either have to reset the tool to the exact same length, within a small tolerance, or you have to end up reposting the job every time you change a tool length. So that's kind of the old way of 5-axis. Linear limits used for approach and retract. One of the functions of the post actually allows us to define a safety box around the outside of our part, and whenever we reposition in tool plane mode or 5-axis mode, really, Mastercam will automatically generate these extra positioning moves. So here you can see that we're retracting to where the tip of the tool is at the intersection of this plane. Then we're moving up to the top. We're reorienting the tool to the new rotary orientation. So that move happens up here in air where it's safe. We move to the next intersection. We move down to where this approach vector intersects this plane. and then we plunge back in. And this is all calculated internally by the post processor. So here's a case where we could program, a contour cut or a drill or a pocket or what have you over here, and then we can program another 3-axis path over here. So we're doing 3 plus 2, and the post will automatically generate these safe repositioning moves for us if we know how to set it up and use it. It's kind of funny. I go through this class with a lot of people, and this post has been around since version 9. And I'm always amazed by the number of people that are too busy to learn, but then they end up going through all of this extra work inside Mastercam, creating, extra dummy tool paths to move stuff around and do all this stuff when they could have the post do the work for them. They don't even know it exists. So it's part of why we do this class. It's to shed light on some of these things. So we talk about the rotary limits, clamping and unclamping, the machine base. So how is the post set up? Basically, is it vertical or is it horizontal? This post will also support horizontal 5-axis machine. So it really does do it all. Miscellaneous reels and integers. So we're at page 87. There's 135 pages. Down at this back section, we get a list of all of the miscellaneous integers and the miscellaneous real numbers that are used in this post, and a description of what they do. And throughout this course, we'll be going and looking at these options and changing values and seeing how it changes the output to the NC file. So miscellaneous integer 2 controls whether we are in absolute or incremental mode. You'll notice the position move at the start is always absolute. But then after tool length comp, so you see the G43 line here, after that you'll notice that we then switch to incremental positioning. So all of these motions are incremental distances from the last move. Miscellaneous integer number 2 controls that on a toolpath by toolpath basis. So for each individual toolpath, you can make a choice about the configuration. Because of, how should I say this? This post is wonderfully complex, but the complexity in some ways is also its Achilles heel. The problem that we run into is there are so many different configurations of 5-axis machines that rather than trying to figure out all of the different permutations that you could possibly need, what they did instead was to give you control over some post functions through the miscellaneous integers and real numbers. So, for example, miscellaneous integers, MI4, start initial primary rotary bias. Plus or minus 999 represents start as close as possible to the limit. 0 represents calculate without using bias. Any other value represents an angle in degrees to attempt to position near. So one of the things that we run into all the time in the world of 5-axis is how do we fit the cut that we're about to do within the rotary limits of the machine. So something that comes up fairly often is cutting a circle. Okay, I just want to take my tool and cut around the outside of a cylinder on a part, and I want to do a 360 degree move. But the issue is I've got a gantry style router that's only got plus or minus 200 degrees of C-axis rotation. So the machine itself is capable of 400 degrees of rotary motion on the primary, but we can't start at 0. So if we start at 0, we're going to hit, C 200 or C minus 200, and then we're going to be forced to retract, unwind, and reposition, and then reapproach the part. What we can end up doing instead is setting our initial primary rotary axis bias to either plus or minus 180. And what that does for us is it allows us to, start at 180, cut through 0 all the way to negative 180, or vice versa, and make a continuous motion cut by forcing the post to start with a different value. MI5 is start initial secondary rotary axis bias. So this is a bias value for the secondary. So when we talk about rotary axes in a 5-axis post, we're often talking in terms of a primary rotary axis and a secondary rotary axis. Typically, the primary has the most motion, although that's not necessarily true. And typically the primary is the one that's going to be unlimited if there is an unlimited axis. The secondary is usually the one that has more of a restriction on rotary positioning, so more limits to how far it can rotate. There are some miscellaneous integers that control how and when the tool retracts. This one happens to control whether our origin is the WCS origin or the tool plane origin. So MI6 says by default we're going to output relative to the WCS always. And a value of 0 says output relative to the tool plane origin. So if we were using G68.2, or maybe we're on a Trunnion style machine, and for every rotation that we do when we lock, we're going to set a new work offset number because we want to have some adjustability at the machine. 7 and 8 control the retract behavior of the machine. Miscellaneous integer 10 is a really cool one. Secondary axis, non-mutating, control. What this allows us to do is temporarily restrict the travel limits or to impose a lesser travel limit on our secondary axis. And a lot of times we use this on a Trunnion style machine where you output the code and you notice the table or the platter is rotating towards the back of the machine away from the operator. And you want to force it to rotate the opposite way so that it faces the operator. And a lot of times we do that with just setting MI10 to either 1 or 2 to force it to stay within a smaller angle range. On the miscellaneous real side, we only use 3 miscellaneous real numbers by default. MR1 is an additional retract and approach clearance at tool reposition. So when the tool repositions between moves, this is where we're going to add a little bit of an approach and a little bit of an extra retract motion. This post processor also has limited support for right angle head attachments for the machine. The limit is that we can only rotate the tool vector perpendicular to the axis of the secondary. So depending on which way your secondary axis rotates, we can support a right angle head attachment with either plus or minus 90 degrees. Now you notice it is right angle head, not compound angle head. So those are kind of the rules, right? It must be a right angle head, and it must not be parallel to the rotation of your secondary axis. If we took this tool over here and tried to put that orientation over here, it would not be valid. So this one, you'll notice the tool points down. This one, the tool points to the left. And that has to do with the orientation of the secondary. In this case, the platter over here is the secondary, whereas the A-axis or B-axis over here is the secondary. In order for us to use the right angle head, we need two more miscellaneous real, well, we need one more miscellaneous real value, and we need the tool length. So what we do is we take the tool length to be the distance from the tip of the tool to the center line of the spindle. And then we take the value of MR10, and that's the z-axis offset from the center line of the tool to the gauge face of the spindle. And these two values basically offset the tool vector back up to where the machine position is. MR6, absolute safe height in Z for unwinds and tool changes. You have to have some different settings turned on in order for that to work. Miscellaneous reels let you shift the position for a 5-axis toolpath. We'll talk about that as well. After we get through the miscellaneous values, there's a section at the bottom of this guide that talks about post customization. So one of the things to look for in the post is these comment markers. Custom changes allowed below, stop custom changes. When we're looking at the post, and if we go up to that tool change section, start a file and tool change setup. Okay. So all of this code that I've highlighted here, P tool change 0, PSOF, P header, P underscore go to underscore start underscore end tool, which is a mouthful to say. It's basically go to the start of a null tool change. And then there's P go to start tool, start up at the actual tool change. So all of these sections here either concern the very start of the post output, so P header, PSOF, or they concern the tool change. And what you'll see is that, for example, here is P go to start tool. Make the tool start up at a tool change. It starts in the first column, which means that that is the post block definition. That's where it starts. And all of these post lines have an indent. Default indent is 6 spaces, and just undo all this stuff. And we'll go back down. Okay. P go to start tool. How are we doing here? Yeah, I got a few more minutes. Okay, good. So we're going to go to the File menu, select Options, And under document settings, I always like to make sure auto convert tabs to spaces is turned on. And what this will do for me is automatically convert anytime I hit the tab key into that many number of spaces. If we look at MP and we look at tabs, I like to set my default tab size to 2. So every time I hit the tab key, I get 2 space characters output because I've got this turned on. By default, MP does not recognize tabs. And in fact, I don't think there's a way, I shouldn't say just by default, it doesn't recognize the tab character. So sometimes you can break the processing if you don't put actual space characters in front. Oh, sorry about that. I had to cough real quick. I swallowed wrong. Okay. One of the other things I'd like to turn on is the white space option here. When we do that, MP puts a little blue dot in the center of every space character. And if I use the tab key, you can see that I'm adding actual spaces, 2 at a time. If we turn off auto convert, you'll notice that instead of, I actually get 2 spaces, or 4 spaces, or whatever I tell it, but you'll notice this arrow character instead of actual space characters. So, something important to be aware of. Make sure that's turned back on here. Okay. Here you can see, this is the start of P, go to, start, TL. Make the tool startup at tool change. And what you can see is that we have 2 post block calls. So P, FD underscore shift underscore inc gets called. And what happens is it jumps to the binned portion of the post, and it makes a bunch of calculations. Then we call P sign ang out for signing the angle. And you'll notice those occur just after P go to start tool. We need those in front of the rest of the stuff that's coming. And that's why you'll notice that there's this marker that says custom changes allowed below. And we have all this code. Unlock rotary axis, tool plane mapping. So this is where we get our G68 code if we're doing, or G68.2 if we're doing tilted work plane. Else, we're either doing 5-axis or regular mode. So we get our normal startup routine. We lock the rotary axis. If we are in tool plane mapping mode, here's where we output our G68 stuff. And then stop custom changes. So you can see that we've got this marker down here, and this code follows the marker. So we definitely don't want to mess up the order of this stuff, and we don't want to get rid of it. It's important. And that's why we have these start and stop custom changes markers, is to let you know, hey, anything that's kind of in between those markers is safe to edit. And anything that's not, really just leave it alone. Otherwise, you might accidentally mess up how the post processes. And the same thing at go to start for the null tool change. Custom changes allowed below. Okay? Stop custom changes. So here we want to make sure that this stuff does execute and doesn't get messed up. And you'll see that kind of throughout the post. Here's PSOF. Custom changes allowed below. Stop custom changes. Okay, we're getting towards the middle of class. We've gone for about an hour now. So I'm going to go ahead and stop the recording. We're going to break it, and we're going to take our mid-class break. So this is typically a 15-minute break, 10 to 15 minutes. I usually try to make sure that we take a full break, just to give everybody a chance to relax, let your brain decompress a little bit. And it's also a good time to ask questions. So if you guys have any questions about the stuff I've covered or questions in general, go ahead, have at it. Go ahead and type them into the little chat box there, and I'll address them when we get back from break, and we'll continue on. Okay? Okay, so I'll see you guys in just